Greetings everyone, this is Professor Roman, and we continue our lectures on linear algebra. It's time now to consider the case where the minimal polynomial of an operator does not split over the base field, and therefore that base field is the real field, since we're considering only real and complex base fields. Let me make a couple of general remarks here before we start. It's my experience in looking at linear algebra books that the division that is made is not whether the minimal polynomial splits or doesn't split, but it's whether the base field is the complex field or the real field. I think that's somewhat of an artificial dividing point. It's the only dividing point that works if you want to speak in very general terms. You can say that any complex matrix is unitarily similar to an upper triangular matrix. You cannot say that about any real matrix, but there are statements you can make about any real matrix. And as we'll see, you can say that any real matrix, square matrix of course, is orthogonally similar to an upper quasi-triangular matrix, and I'll explain what that means in short order. But the real issue is not whether the base field is complex or real. The real issue is whether the minimal polynomial of the matrix under consideration splits or doesn't split over the base field, whatever that field is, whether it's real or complex. So that's the way I've chosen to structure this course and my book. But I don't know whether you'll see this elsewhere. I have not seen it elsewhere. Another, I guess what you might call, advantage of the split using real and complex fields is that some books on linear algebra, perhaps most at the undergraduate level, even at the upper undergraduate level, don't even cover the real case. I think that's a shame, because while the statements of Shures Theorem and the Spectral Theorem are a bit more complex in the real case, the theory that the analysis that arrives at those theorems is the same, with one slight complication. And I think if it's phrased in the right way, the complication doesn't look that bad at all. And I'll let you be the judge of that as we get to it. The issue now is that since the minimal polynomial, we will assume, does not split over the base field, the real field, we must deal with irreducible quadratic factors of the minimal polynomial. So linear deflations will not be sufficient in this case. We're going to need to discuss what I am calling a quadratic deflation to cover that extra case. Let me give you an overall sense of how this is going to go. First, let's recall that a linear factor, x minus lambda 1, say, of the minimal polynomial of a matrix gives us an eigenvalue, lambda 1. And if we let u sub 1 be a unit eigenvector associated with lambda 1, then u sub 1 by itself spans a one-dimensional, A-invariant subspace of Fn. A is our matrix under question. We can then extend this vector u1 to an orthonormal basis for Fn, and that gives us a linear deflation. So this is old news from the last lecture. We can continue the deflations by applying them to the residual matrices to eventually produce an upper triangular matrix that's unitarily similar to A. We call this a Shures form of A, because there are many possibilities for a Shures form. And that is the statement of Shures Theorem. The Spectral Theorem tells us that the Shures forms of the matrix A will be diagonal. All of them, in fact. If one of them is, they all are, if and only if A is a normal matrix that commutes with its adjoint. A remarkable theorem. So that's the situation in a nutshell that we have discussed for the case when either the minimal polynomial splits, or at least there's a linear factor, so we can do a single linear deflation. That still applies even if the minimal polynomial doesn't split. If it has a linear factor, we can still do a linear deflation, and we will. If the minimal polynomial of A has an irreducible quadratic factor, which I'll call Q of x, then linear deflation will not work on Q of x. But as we will see, there is a quadratic deflation that's not that much more complicated and that does work. A linear deflation in the final matrix produces a row and a column that look like this. There's in the column, this is the main point. In the column, we find lambda on the diagonal, and below it all zeros. And so we are headed towards upper triangular geometry. Quadratic deflation will do something similar, but 2 rows or 2 columns at a time. And below, in both those columns below, will be all zeros. Well, you see what's happened is that this entry C, which will be non-zero because Q of x is irreducible, lies below the main diagonal of the matrix. So whenever we require a quadratic deflation, and we will require at least one, we destroy the upper triangular geometry, but in a way, only slightly, a non-zero entry in the main sub-diagonal. In another way, it's a disaster because it hides the eigenvalues, it makes matrix algebra more difficult. It's a major problem. But this is the best we can do. This 2x2 matrix, which I've isolated here, is not unitarily similar to a 2x2 upper triangular. In other words, there's no way to get rid of this non-zero entry below the main diagonal in the sub-diagonal. We're stuck with it. So it is, in some sense, you might say, irreducible. And we'll come back to that term. It's irreducible because the quadratic factor is irreducible. So the upshot is we're going to have to settle for a somewhat more complex matrix geometry when dealing with minimal polynomials that don't split. It's close to upper triangular or close to diagonal in the case of the spectral theorem, but it does dip into the main subdiagonal for the upper triangular case, and both the main subdiagonal and the main superdiagonal in the quote diagonal unquote case. And we'll get to all the details. I just wanted to give you an overview so you see where we're headed. The terminology gets a little awkward, upper quasi-triangular, quasi-diagonal, and sometimes it takes a little bit of time to adjust to that terminology. Even I find myself saying quasi-upper triangular instead of upper quasi-triangular on occasion. So if I do that, I apologize now. This table, which I'll show you again when we're done with this conversation, summarizes what's going on in both cases. When the minimal polynomial splits, all matrices are unitarily similar to an upper triangular matrix, and the normal matrices are unitarily similar to a diagonal matrix. That's the best scenario. This is the one that will be covered in, I would imagine, all serious upper division linear algebra courses. When the minimal polynomial does not split, all matrices are unitarily similar to what we will call an upper quasi-triangular matrix. Quasi, according to the dictionary, means almost but not quite. In the case when the minimal polynomial doesn't split, the normal matrices, the real normal matrices, are orthogonally similar to what are called, what I am calling, Shures block quasi-diagonal matrices. The adjective Shures block refers to the fact that the little 2x2 matrices that end up on the block diagonal do have a very nice form. The diagonal entries are the same, and the off-diagonal entries are negatives of each other. And I am referring to this as a Shures block. It's S-C-H-U-R, not S-U-R-E. Okay, so now we can get down to business here. Incidentally, the term quasi-diagonal and upper quasi-triangular do appear in the literature. They're not my invention, but they don't always appear in treatments of this material. So if you say to someone quasi-diagonal, you may have to explain yourself, give the definition, which is where we are headed right now. The first step is a preliminary definition. A real 2x2 matrix A is irreducible if its characteristic polynomial is irreducible over R. It's easy to spot the irreducible matrices because characteristic polynomial is just a quadratic. This is the discriminant of the characteristic polynomial. It must be negative in order for the polynomial to be irreducible over the real field. This is the sort of matrix we will encounter where the diagonal entries are the same. This matrix is irreducible if and only if the product of the off-diagonal elements is negative. So this matrix, which we'll encounter as well, is irreducible as long as B is non-zero. Here's another example of an irreducible matrix. Now I have a confession to make. The term irreducible does have a more established meaning in matrix theory. I'm borrowing this term. It's not standard, at least as far as I know. But the more established use of the term irreducible when applied to matrices is done in very advanced matrix theory. So we're not going to have anything to do with that, and there'll be no conflict. So within the confines of this book and this course, we will use the term irreducible in the way I have just done. And there'll be no conflict. And chances are, if you encounter someone and you want to discuss this, they won't even know about the other use of the term irreducible. But you still should say, this is a borrowed term, so there can be no confusion. The Cayley-Hamilton theorem tells us the minimal polynomial of an irreducible matrix divides the characteristic polynomial, and so it must be equal to the characteristic polynomial. And I'll let you sort that out. Matrices whose minimal and characteristic polynomials are equal are referred to as non-derogatory, something we'll discuss briefly in a later lecture. So here is the new matrix geometry that we are dealing with in this particular case of the non-splitting minimal polynomial. A real matrix A is quasi-diagonal if it has the block diagonal form here. I didn't write the word block here. At some point, you need to recognize block matrices without that symbol, because I think I'm the only one who uses it. Each diagonal block is either a 1 by 1, and I represent that by the lambdas here, or an irreducible 2 by 2. And there is at least one irreducible 2 by 2 block. And I'll comment further on that in a minute. The order in which these diagonal blocks appear is not important, really, but I have standardized it, and I think it's somewhat customary that the 1 by 1 blocks come first and then the 2 by 2s. A real matrix A is upper quasi-triangular if it has this form here. The diagonal situation is the same, but there can be non-zero entries above these diagonal blocks. And again, there must be at least one 2 by 2 block. Here are two examples, just for concreteness. This is a 5 by 5 quasi-diagonal matrix. This is a 1 by 1 block on the diagonal. These are 2 by 2s, and they are irreducible. The entries on their diagonals are the same, 2 and 2, and the product of the other entries is negative in both cases. Here is an upper quasi-triangular matrix. Same story about the blocks on the diagonal, but there's a non-zero entry in the space above those diagonal blocks. The requirement I made that quasi-diagonal and quasi-triangular matrices have at least one irreducible 2 by 2 block is designed so that diagonal matrices are not quasi-diagonal and triangular matrices are not quasi-triangular. Quasi, as I said before, means almost but not quite. That's not the reason I made this requirement. The reason is just that it makes the exposition simpler. Instead of having to say quasi-diagonal but not diagonal multiple times in the coming discussion, I don't have to do that now. I can just say quasi-diagonal, and you know that it is not diagonal. So it's just for exposition purposes. Okay, so let's look at the quadratic deflations. As we did before, we'll speak in matrix terms. Let A be an n by n matrix over the reals. What we need is to produce an invariant subspace from a quadratic, an irreducible quadratic factor of the minimal polynomial. It'll be a two-dimensional invariant subspace. How does one do that? Well, let A be an n by n real matrix, and let Q of x be an irreducible quadratic factor of the minimal polynomial. And suppose that mu is a non-real root of gee, I didn't say of Q of x. And suppose, oh, I did say it, just worded it differently. Okay, so I don't need this. So mu is a non-real root of Q of x, therefore of the minimal polynomial. And so we'll write it as a plus ib, and b is non-zero. And z is a complex eigenvalue, u plus iv. So we are thinking of A as a complex matrix now. It's a real matrix. We think of it as a complex matrix. It will have an eigenpair that looks like this. Then the subspace spanned by the real and imaginary parts of the complex eigenvector. So these are real vectors. They're not eigenvectors. In the linear case, we got an eigenvector. Here we get the real and imaginary parts of a complex eigenvector. This subspace is a two-dimensional A invariant subspace of Rn. So that is the additional complication in passing from cases where the minimal polynomial splits to cases where they don't. We can't just grab an eigenvector and we're off to the races. We have to upgrade the matrix temporarily to the complex world, grab a complex eigenvector, then take its real and imaginary parts. When we apply the matrix A to those two real vectors, we'll get these equations. And so the matrix representation of the restriction of A to this subspace using the basis UV is this very nice looking 2 by 2 irreducible matrix. And the proof is quite short, really. Starting with the eigenvalue equation for the complex eigenvalue-eigenvector pair, write this out in real and imaginary parts, and comparing the real and imaginary parts gives us these two equations, and therefore this matrix, once we show that u and v are linearly independent. That's all we have to do. Okay. But if we suppose to the contrary that v is a real scalar multiple of u, then the two equations we got look like this. If r is 0, well, then we have a problem. bu becomes 0, but b is not 0, so u is 0, and therefore v is 0, and therefore z is 0, and that's not possible because z is an eigenvector. So r is non-zero, and we can multiply both sides by r inverse. Get these two equations, compare, the left sides are equal, so the right sides are equal, so these scalars are equal, which tells us that negative r is r inverse, and that's not possible for a real number. So that's the whole proof. Okay, okay. So this is how we're going to deflate a matrix using an irreducible quadratic factor of the minimal polynomial. What we have to do to implement the deflation is we have to take this basis uv for this two-dimensional A invariant subspace and orthonormalize it, get an orthonormal basis for that subspace. Now this will change the matrix representation if we use that orthonormal basis. Let's call that matrix representation B. This was the matrix representation we had before that looked very nice. So we're going to lose this nice form, unfortunately. But a change of basis means that the two matrix representations are similar, not necessarily unitarily similar, but similar, because the basis uv was in general not be orthonormal. So we'll get some matrix representation B, but it'll be an irreducible matrix. And so A is then, when we take the matrix representation of A with respect to extend the two-dimensional orthonormal basis to a full orthonormal basis, the matrix representation will have this block form. B here is now a 2 by 2 irreducible. Zeros below, don't know what's going on here, residual matrix. So the pattern is exactly the same. In the linear deflation, B was a 1 by 1 matrix. In a quadratic deflation, it's an irreducible 2 by 2 matrix. This all should make perfect sense. Irreducible quadratic factor, irreducible 2 by 2 matrix, or submatrix. So that's the story on quadratic deflations. Now we can repeatedly deflate using the minimal polynomial to arrive at Shures Theorem. And since we always strive to be as neat and tidy as possible, we'll do it the following way. Factor the minimal polynomial into primes. So group them together. These are the linear factors raised to whatever power they occur. The order doesn't matter here, but we'll fix the order. Next come the irreducible quadratic factors to whatever their powers indicate. Okay. And just as before, we do the linear deflations first, if there are any. There may or may not be any linear factors for the minimal polynomial, but there is at least one irreducible quadratic factor because we're assuming the minimal polynomial doesn't split. Well, we do the linear deflations first in the same order we used before, and then we do the quadratic deflations, and this is what we will get. We'll first exhaust the first eigenvalue, if there is one, lambda 1s, however many times as indicated by the geometric multiplicity. Then come the 2 by 2 irreducible blocks. There's got to be at least one. So this one must appear. Whether there are any more B1s depends on the situation. Whether there are any other 2 by 2s also depends on the minimal polynomial. This we will again refer to as a Shures form of A, or anything orthogonally similar to A as a Shures. Okay, but be careful here. Any matrix of this form that is orthogonally similar to A. And the issue of the order of the blocks here, again, is not important really, but you certainly can't say which lambdas precede which other lambdas, or which blocks appear before which other blocks. I just like to group the identical lambdas together and group the identical blocks together. The operator version says that a real finite dimensional linear operator whose minimal polynomial doesn't split has an upper quasi-triangular matrix representation via an orthonormal basis. And that's a Shures form for the operator. As in the prior case, the spectral theorem tells us which real matrices whose minimal polynomial doesn't split have a quasi-diagonal Shures form. And the analysis is very similar to what we did in the somewhat simpler case. Here is an upper quasi-triangular matrix. We want to know when does the asterisk represent only zeros, so we get a quasi-diagonal matrix. And again, we'll let the entries of this matrix be written as Bij. And we have some insight now in what is likely to be the characterization, and that is normality. So let's assume that M is real normal. Since we're dealing with real matrices, the adjoint is the same as the transpose, so M commutes with its transpose. And let's look at the first deflation that it produced this matrix. If it was linear, and so if this lambda 1 actually exists, remember the lambdas don't have to be in this matrix. There may not be any of them. But if there is one, then we just do a linear deflation, just as before. And it'll produce row and column that look like this. If the first deflation was quadratic, or if in the repetitive process of doing deflations we first encounter a quadratic diagonal block, but I'll assume it's the first block just because the notation would get really ugly otherwise. So here is this 2 by 2 block. We don't know what's going on over here in the rest of the rows. We know zeros below. And here is the transpose. Now in the linear case, we looked at the first entry, the upper left entry, and we got two equations in the two products, M transpose and M transpose M. And we got two results. We equate them. Things were pretty simple. Everything over here canceled. And we saw immediately that there was a row of zeros. This time, however, when we look at that entry, we get this equation and this equation for the reverse product. But this has two terms, and this second term does not appear over here. Well, it's not unreasonable. We're dealing with a 2 by 2 matrix. One equation is not going to give us what we need. It's going to take a second equation. So we look at the 2 entries, the next entry on the diagonal of M transpose and M transpose M. We get another set of equations equating these two values. Actually, we're going to equate, let's see. these two are equal and these two are equal. So the fact that these two are equal, there is a little bit of cancellation. The first term here cancels, and we'll get this equation. In this case, it is the b22 term that will cancel over here, and so we'll still have the b12 term, and we'll be missing the b22 term over here. So we'll get this equation. We have these two equations now. And we can take this value, which appears right here, and replace it by all of this, and we'll end up with this equation that looks like this. Now we have a further cancellation. This will cancel with this. And so all the other terms, since they appear squared, if that sum is 0, every individual term is 0, all of the b's are 0, and so all of these entries in both rows are 0. Same principle as before, just algebra is just a bit more complicated. So we can repeat the process by looking at the submatrices M1 and M1 transpose. Same algebra applies, and we finally arrive at a quasi-triangular matrix. So if the original matrix, if the matrix M, the upper quasi-triangular matrix M, is normal, it's quasi-diagonal. But there's something else here that's very important. This matrix is also normal. Okay. It's the same matrix as the original M. Okay. So the diagonal matrix, quasi-diagonal matrix, is normal, which means each of these blocks is normal. Each of these is an irreducible normal matrix. Let's say, I shouldn't have used A here. I should use B. Let's say B looks like this, and it's irreducible and normal. The normality condition gives these two equations. Just work out the matrices here, the matrix products, set them equal. The irreducibility condition we've seen before is this discriminant is negative. Well, the discriminant being negative means BC here must be negative. If it was 0 or positive, since this is 0 or positive, this would be false. So BC is negative, but B squared equals C squared, so C and B have to have opposite signs. They have to be equal, but of opposite sign. And then the second equation here, when you use this fact in the second equation, you will discover that A and D have to be equal. And we recover the nice 2x2 form that we lost in, under Shures Theorem. When the matrix is normal, we don't lose it. I'm going to call these Shures blocks. I don't know whether anybody else does or not, frankly. But I will reserve the notation HAB for these blocks. So we have shown that a real 2x2 matrix is irreducible and normal if and only if it's a Shures block. I didn't do the converse here, but I'm going to leave that for you. that this matrix is both irreducible and normal. And so what we get here when we have an upper quasi-triangular matrix that is in fact normal, we get not only quasi-diagonal, but quasi-diagonal where the irreducible blocks have this very nice form, which we're calling a Shure block. So I'm going to call this Shure block quasi-diagonal. I know the terminology is kind of a downer. There's a lot of it. This quasi word keeps coming up. I don't know how to avoid it. It could be worse, frankly. A matrix that's unitarily similar to a diagonal matrix is said to be unitarily diagonalizable. I have avoided saying unitarily quasi-diagonalizable and unitarily upper quasi-triangularizable. So actually, in an earlier draft of the book, I had those terms, and I thought that was just a little overwhelming. But I think that I found sort of a happy medium that's going to displease everybody, but as little as possible with the terminology. I just don't know how to make this terminology any simpler than it is, but I recognize that it's a little bit difficult. Shure block quasi-diagonal is a mouthful, but that's the way it is. I mean, it's quasi-diagonal, and the irreducible diagonal blocks are Shure blocks. I suppose I could have called them nice form blocks instead, but it just seemed to be the terminology that works the best. So here is the analog of this theorem here, this theorem 8.10, in the case where the minimal polynomial splits. And here's the corresponding picture. An upper quasi-triangular matrix, M, is Shure block quasi-diagonal if and only if it's normal. So normality allows us to, I guess it depends on how you think of it, upgrade or downgrade, I don't know. Let's say upgrade quasi-triangular to quasi-diagonal. And we can express that in terms of similarity classes. An orthogonal similarity class whose minimal polynomial doesn't split is normal. In other words, the minimal polynomial, all the matrices are normal in the class, if and only if all of its upper quasi-triangular matrices are in fact quasi-diagonal. A real finite dimensional linear operator whose minimal polynomial does not split has a Shure block quasi-diagonal matrix representation with respect to an orthonormal basis, if and only if tau is normal. The normality allows us to replace upper quasi-triangular with quasi-diagonal of a particularly nice form, Shure block quasi-diagonal. Here is the embellishment of the spectral theorem in the case where the minimal polynomial doesn't split. The following are equivalent. A is real normal. A is orthogonally similar to a Shure block quasi-diagonal matrix. Here's where I could say A is Shure block quasi-diagonalizable, but I didn't. And these 2 by 2 irreducibles are Shures blocks, so they have this form. Fn is an orthogonal direct sum of this form. In the linear case, in the case where the minimal polynomial splits, we just had eigenspaces here. But now we must content ourselves with at least one two-dimensional subspace, A invariant subspace, so submodules in the language of operator modules, with an ordered orthonormal basis that gives this representation for the matrix restricted to these subspaces. Here's the operator version, which I won't go through now. It's the same thing, but we have to say the operator is represented by a Shures block quasi-diagonal matrix. Otherwise, it's the same. Here's the summary again. This is the same table cut and pasted from the earlier discussion, but we now have justified this. And here's the Shures block quasi-diagonal. So that's the story on what happens when the minimal polynomial doesn't split. It is definitely more complex than the complex case, than complex space field case, but I would like to submit that it's, and it may seem very confusing right now, the first time you go through it. That's certainly understandable. But the wrinkle is only in the fact that we end up with these 2 by 2 irreducible blocks on the diagonals rather than all 1 by 1 blocks. And what we're going to do next, it's clear from the spectral theorem, in either case, in both cases, that normal matrices and normal operators are very important. So we're going to take a closer look at normal operators and special types of normal operators, such as self-adjoint and unitary operators. That will be coming next.